Hello, 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 everybody. Root Beer here, and we have made it to the end of the 2007 Grade 11 Fermat paper. We're here. It's question number 25. Now, hopefully, you have tried this question before watching this video. Practice really does make perfect, and you only find your own mistakes when you actually try the questions rather than just watching my videos and saying, yep, I knew that, yep, I knew that, oh, yeah, that's obvious, oh, therefore I could have done the question. No. Try them for yourself. If you need to, pause the video, come back after you've tried question 25. Okay? Good? Alright, let's get into it. So, in theory, this is the hardest question on the contest, but I mean, all of Part C is challenging, so it all depends on what type of concepts you like, and which ones you don't. So, question 25, what have we got here? How many ordered pairs, BG, of positive integers with 4 less than or equal to B less than or equal to G less than or equal to 2007 are there, such that when B black balls and G gold balls are randomly arranged in a row, the probability that the balls on each end have the same color is 1/2. Interesting. So, I would think if B and G are equal, that would certainly be a situation we're looking at, but maybe there are other ones, and maybe I'm misunderstanding, and B equal to G isn't one of the ones we're looking for, but I think... Actually, no, if B equaled G worked, there'd be close to 2,000, but if I look at my answers, I'm looking at 58, 59, 60, 61. I don't know why they don't have these in order, but whatever. So we're looking at something between 58 and 62. Okay, that's interesting. Interesting. What possible patterns for B and G's could make that? Well, let's see if we can just... they're asking about probability. Let's see if we can just get this probability in terms of B and G. You know, maybe there'll be some sort of 3G minus 2B has to be equal to 0 or something, and that'll narrow down our possibilities. Okay. So if we have B black balls and G gold balls, probability is number of desired outcomes. In this case, the end balls are the same color over the total number of outcomes. So how many ways are there to arrange B black balls and G gold balls? Actually, that's a good question. How many ways are there to arrange B black balls and G gold balls? Well, if I had 2 black ones, we could have black, black, gold, black, gold, black, or gold, black, black. Not especially helpful. Okay, I think yeah. So, there are B plus G balls in the lineup. G of them must be chosen to be gold. Therefore, there are B plus G, choose G, different lineups. Okay? These are binomial coefficients. They are useful to know. If you don't already. I know some of the high school curricula drop these sorts of things, but they're useful to learn on your own. And I'm going to be exploiting them. Basically, N, it's spoken as N, choose K, and it's the number of ways, if you have 5 things, selecting 3 of them. I have B plus G sort of spots in my lineup. I am selecting G of them, and I'm saying these are where the gold balls will go. That's the idea. Okay, so that's the bottom number. B plus G, choose G. It could also be B plus G, choose B. You could choose where the black balls go. It's the exact same number. Okay? 5 choose 2 is the same as 5 choose 3. Alright, so that's the bottom number. That's the total number of outcomes. Now, if I want the end balls to be the same, I have two cases. So the black end balls, so if I have black balls at the end, I'm choosing that. How many ways are there to do that? Well, there's the two end balls are fixed black. And fortunately we know that there are at least 4 black balls, so what's left over? What choices can we make? We can't choose the end balls, but we can choose everything in the middle. And that's B plus G minus 2. And again, we'll just choose G of them to be gold. Okay. That's not so bad. And that's if we had black ends, and those would be the same. But what if the two end balls were the same, but they're gold? That's a different case. So 2 of the gold balls would be selected and forced to be at the end. And there'd still be B plus G minus 2 balls in between. And we have to choose, if we're choosing the gold ones, now we're choosing G minus 2 of them. Alternatively, we could just say we're choosing the black ones. That would be fine as well. Doesn't really matter. We've been using gold the whole time, so I'll just stay consistent. There are G minus 2 gold balls left. We started with G of them, but then we took 2 of them and forced them to be at the ends. Okay? So our probability is going to be B plus G minus 2, choose G, plus B plus G minus 2, choose G minus 2, out of B plus G, choose G. Now we can use the formula for these coefficients. N factorial over K factorial times N minus K factorial. And what will we have? We'll have B plus G minus 2, all factorialed, over G factorial B minus 2 factorial, because we took 2 of the black balls out and put them at the ends, plus B plus G minus 2 factorial over B factorial G minus 2 factorial. And here we have B plus G factorial over B factorial G factorial. Alright, so we could get to simplifying. One thing to note, B plus G factorial is B plus G times B plus G minus 1 times B plus G minus 2 factorials, based on the definition of factorial, which we maybe remember, n factorial is just n times n minus 1 factorial. We recursively build up factorials. Okay, so knowing this, we could certainly simplify our probability a little bit. So we'll have the B plus G minus 2 factorial on top. I'm going to write it as G minus 1, G minus 2 factorial, B minus 2 factorial. Separate those out a little bit. Plus B plus G minus 2 factorial over B minus 1, B minus 2 factorial, G minus 2 factorial. So you see I'm making, I'm trying to get as much in common with the top and the bottom as I can. So we have B plus G minus 1, and then B plus G minus 2 factorial, all over B minus 1, B minus 2 factorial, G minus 1, G minus 2 factorial. So now what can I do? Well, I can take out a factor of B plus G minus 2 factorial over G minus 2 factorial, B minus 2 factorial from the top and the bottom. That cancels, that cancels, that cancels, that cancels, that cancels, 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 cancels. And what expression am I left with? 1 over g minus 1, plus 1 over b minus 1, all over b plus g minus 1, over g minus 1, b minus 1. I got rid of all the factorials, so that's at least a plus. Now the top, I could get a common denominator there. We'll do b minus 1 plus g minus 1, all over b minus 1, g minus 1. And the whole thing is over b plus g minus 1, over g minus 1, b minus 1. And some more stuff cancels. And we're left with b minus 1 plus g minus 1, all over b plus g minus 1. So this is always the expression for the probability. I really think that's about as good as it's going to get. Maybe we'll need to expand these, but I'm going to leave them like they are for now. But no matter what b and g we pick, that's the probability. Okay? So we've done that. We've gone as far as we really can analyzing just the basic probability setup with the question. Now they're specifically asking for b's and g's that satisfy an extra condition. Namely that this probability here, the one that we just worked out, is equal to 1/2. Okay, that's what we need to now deal with. So we can set this probability equal to 1/2. I'll set that up on the next page. So we got 1/2 is b minus 1 plus g minus 1, b plus g minus 1. Well, it makes sense to cross multiply. We get b plus g minus 1 is 2b minus 1 plus 2g minus 1. I'm not seeing anything immediately obvious that we should do here, so I guess expand everything out. So b squared plus bg minus b plus bg plus g squared minus g is 2b squared minus 2b plus 2g squared minus 2g. Let's see, we can... So we get 2 bg's here. I can bring the b's and g's over to the other side, so this will be b plus g, and then the b squareds and g squareds come over here. Okay, b plus g is b squared minus 2bg plus g squared, but this is b minus g all squared. Oh, now that's interesting. B plus g is b minus g squared. That's an interesting expression there. When can that ever happen? Can I think of a really obvious and stupid way for this to... So what if this were 3 and 1... Actually that does work. 3 and 1 does work. So 2 squared is 3 plus 1. So b is 3 and g is 1 works. Except, I guess they all have to be bigger than... Yeah, they have to be bigger than 4. Surely there should be... I mean, there's probably some formula, but... I like it. I like it as a formula, but I can't see a nice way to sort of set it up. So what I'm going to do is I'm instead going to treat it as a polynomial in b. So we'll get plus g squared minus b minus g is equal to 0. Just rearranging it. We'll group the b terms together. So plus, minus 2g plus 1, and then plus g squared minus g equals 0. And quadratic formula, maybe? So negative b plus or minus square root of b squared minus 4ac all over 2a. And it'll be 2g plus 1 plus or minus. Now, incidentally, the g squared here and the 4g squared here, those will cancel out. And square root will have minus 4 negative g, so it'll be 8g plus 1 all over 2. Okay. The plot thickens. Interesting. So I need 8g plus 1 to be a square. And I'm betting that there's roughly maybe, so 2007 times 8 square rooted should be roughly 62 or 60 or whatever it is that we were talking about. Well, let's find out. 8 times 2007. Just grabbing my calculator here. 126. Interesting. That's about twice. That's twice 63. So maybe it's every other one. Okay. So let 8g plus 1. Obviously, this has to be odd. So let that be 2k plus 1 squared. It's an odd square. So if that's the case, then we get 2g plus 1. We'll have to go with the plus 1, I would imagine. Maybe not. I'm going to change this to 2k minus 1. Nah, 2k plus 1's fine. But we'll have 2g plus 2k plus 2 all over 2, or 2g minus 2k all over 2, which is really just b. So that would be b is equal to g plus k plus 1, which it can't be, because b is less than or equal to g, so this is impossible. Or b is g minus k. And that should be the one we work with. Alright, so let's see if this works out. So I want an odd square, so 8g plus 1 is an odd square. That's fine. What would be a good odd square? Let's try 25 squared. So k is 2. G, so that would be 5 squared is 8g plus 1. So g is going to be, well, that's still too small. Let's try k is 5. So 2k plus 1 is 11. 121 is 1 plus 8g. G is 15. So b should be 10 in theory. Okay, so does that work? B plus g is b minus g squared? You betcha. Okay, does it work for our whole probability? So that was b times b minus 1 plus g times g minus 1 all over b plus g times b plus g minus 1. So this is 90 plus whatever 15 times 14 is, just grabbing my calculator, 210. And then 25 times 24, 600, and yet 300 out of 600 is 1/2. Okay, so this is looking really, really good. And 2k plus 1 squared, by the way, is always of the form 8 integer plus 1. We can show that 4k squared plus 4k plus 1. So it's got a factor of 4. And then if k is odd, its square is odd. Odd plus odd is even. If k is even, its square is even. Even plus even is even. So there's definitely a factor of 8 here. So as long as I take any square, or any k, I can do 2k plus 1, square it, I can get g, and then g subtract k should be b. Alright. So, I can get everything in terms of k here. So, for any k, g is 4k squared plus 4k over 8, which is just k squared plus k over 2. And b is g minus k, which is k squared minus k over 2. Okay, so for k being 5, we had 25 plus 5 over 2 is 15. 25 minus 5 over 2 is 10. Now, we want our b's and our g's to be in this particular range. All right, well, on the low end, we need 4 to be less than or equal to b, which is k squared minus k over 2. So that means 8 is less than or equal to k squared minus k. I would think we can probably just sort of reason our way through this. 5 is fine. 5 squared minus 5 is 20. How about 4? 4 squared minus 4 is 12. That's fine. 3 squared minus 3. So k has to be at least 4. Okay. Now for this one here, g is no bigger than 2007. And of course, g is equal to k squared plus k. So k squared plus k is less than or equal to 4014. I'm less inclined to believe that I can just sort of wing that one. So I'll do some guess and check with my calculator here. What's close to square root of 4014? 63. Okay, so let's try 63 squared plus 63. 4032. How about 62 squared plus 62? 3903. So k is going to be at most 62. Combine both of these facts. Any k between 4 and 62 inclusive will work. So since it's inclusive, we do 62 minus 4 plus 1. So that'll be 58 plus 1. Or 59, and that will be our answer. It's one of them. It's E. There we go. So we're saying the answer is E, 59. We could even double check these extreme cases and the ones below it. I've got time, so I'm going to do that. I've shown that any k will work. What if k is equal to 3? Well, we'll have b is 9 minus 3 over 2, which is 3, and that's a bit of a problem. So it says right here, b is at least 4. Okay, so that wouldn't work. But k being 4, b would be 16 minus 4 over 2, so that's 12 over 2, that'd be 6. And g would be 16 plus 4 over 2, which would be 10. 10 minus 6 is 4, 10 plus 6 is 4 squared. At the other end, k is 62, so that would be b is 62 squared, I don't know off the top of my head. So we'd have 3,782. Divide that by 2. 1891 for B. G in this case would be 62 squared plus 62. Divide that by 2. And we'd get 1953. 1953 minus 1891 is 62, which when we square it, we get 3,844 minus 1891 is 1953. And if we do K as 63, this should fall apart. So we get B is 3,906 divided by 2. 1953. Hey, it's the next number. Oh, that's pretty cool. I just realized that. It's always the next number in the sequence. Because we had 6 and 10, and then it'll go to 15, and then who knows where it goes from there. But now 63 squared plus 63 is 4,032 divided by 2 is 2,016, which is just out of our range, so that won't work. So yeah, it is 62 minus 4 plus 1 to include the last one, and that's 59. So we have our very final answer, and that'll be E. And that wraps up the Fermat contest. So that's the last of the multiple choice contests that we're going to go through from Waterloo in the year 2007. Of course, there are still other contests. The Hypatia is written for a written solution contest for grade 11. And of course, the ever popular Euclid to look forward to. I'll be uploading that at some point in the future as well. So stay tuned for the 2007 Euclid. And yeah, until then, keep poking around. I've got other Fermats and other things up there, and you might find another contest that you'd like to go through. I will see you guys for that, whatever it may be.